So this webinar is what is measurement traceability. Today's topics will cover the following. We're going to cover metrological traceability. We're going to cover some common force measurement errors and the importance of calibrating the instrument in the manner it is being used. And we're going to dabble a little bit on measurement risk. As I said, we have that full webinar on measurement risk. So if that's of your interest, I encourage anybody to sign up for that one. That's an ongoing webinar. It's very important, and it's ongoing. So the learning objectives for today, by the end of this presentation, the goal is to understand the metrological traceability hierarchy and to think a lot differently about calibration. This is me. My name is Henry Zumbrun, president with Morehouse Instrument Company. I've been here for about 20 years. If there are any questions, I sent an email out to people at the beginning of this. If there are any questions, please feel free to email me. Website www.mhforce.com. And if you want a PDF copy, please send this email. This is being recorded, so if anybody listening wants it, just that email is good. I'm happy to send PDF copies. So a little bit of noise. So I will mute everybody, and then I'm going to ask if you use the chat bar. So measurement traceability. Measurement traceability is really composed of 7 essential elements. The first of those elements is reference to International System of Units, SI units. Several people say, I need something that's NIST traceable. Well, NIST traceable is not really the proper term to do any of this. It's really traceable to SI through NIST or through an NMI. That's what we want to say. NIST traceability does not do what we need it to do, and we will go over that in a few slides. The second element is an unbroken chain of comparisons. The third is measurement uncertainty. The fourth is competence. The fifth is documentation. Sixth is calibration intervals. And the seventh is measurement assurance. And measurement assurance really holds everything together. And we're going to break these down. We're going to break these 7 elements down and discuss one-on-one what each of them are. So let's start with reference to International System of Units. So SI units, per NIST SP 811, reference to SI units, the chain of comparison must, where possible, end at primary standards for realization of SI units. For force, it's simple. We have the kilogram. SI base units are a choice of 7 well-defined units which by conventional are regarded as dimensionally independent. These units are the meter, the second, the kilogram, the ampere, the Kelvin, the mole, and the candela. It's interesting that the only one that's left that actually has an artifact is the kilogram, and the kilogram is being redefined. There's lots of information on YouTube. There's some cool things about a perfect sphere and some other things. So about that, if you're interested, you can do a YouTube search. But any of these elements make up other units. So for force, the reason meter, second, and kilogram are bolded or now highlighted is because these are the elements that make up what we do, which is force measurement. They also make up torque measurement, which we do as well. So these three elements combined make up those. So make up of the derived units. And the derived units are formed by combining the base units according to the algebraic relations linking the corresponding quantities. So down below here, you have force equals mass times acceleration, which is meter per second per second squared. Then we go to number 2, which is metrological traceability. And this is the property of measurement result whereby the result can be related to a reference through a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. That's defined by the VIM section 2.1. There's a link. If you get the PDF, you can click the link to the VIM. VIM is the International Vocabulary of Metrology. So this is going back to traceable to NIST. What does that really mean? Not much. It's got to be traceable to SI units. And then we go to the measurement uncertainties relation to measurement hierarchy. So everything starts really at the BIPM or SI units. And then it goes down to a National Metrology Institute. Can be NIST. NIST is in the United States. Can be PTB. That's in Germany. Can be CNOM. That's Mexico. NMIJ is Japan, and on and on and on. Most people are probably familiar with NIST. So NIST is the NMI of our country. And then there's primary reference laboratories. There's those labs that have capabilities and sometimes better than their NMIs, and in some cases not as good as the NMIs. For primary reference laboratory, the typical uncertainties for force are over at the right. NIST is the best. They're the best in the world. They're the only ones with a 1,000,000-pound dead weight frame. They just took it apart and rebuilt it, and they can realize uncertainties of 4 to 5 parts per million. Morehouse is a primary reference laboratory. We had our weights calibrated by NIST. They were corrected for gravity. They were corrected for density and air buoyancy, and we can realize about 0.0008%, 8 parts per million for one standard deviation. And then typically after us, the people that we service are the accredited calibration suppliers. Those are working standards, and even those making field measurements. We do a lot of calibration related work for them. So the way that works is every step or chain link down, the uncertainty gets larger. It's pretty simple, and you can see on the right how it grows. So typical accredited calibration suppliers are around 0.02%, working standards 0.1%, field measurement 0.5%. Double these, people making tests to ASTM specification E4 are usually at 1% for force. So if we examine this in greater detail, the BIPM is the highest level on the chain of traceability where the 7 SI units are realized. From the BIPM, the international prototype of the kilogram, an artifact made of platinum iridium, is kept at the BIPM under controlled conditions specified by the first CGPM in 1889 when it was sanctioned the prototype and declared. Now, they keep this one. Our NIST, I believe, has 3, if I'm not mistaken. They may have more, and other NMIs. So they keep them, they compare them all, they go back for calibration, they compare them all, and this disseminates the unit of mass. And then we get to National Metrology Institute. In the United States, we have NIST. It's the designated NMI. In Mexico, you have CNOM. And then from there, we have primary reference laboratories. A lot of these are government or commercial. Some are commercial laboratories that have invested a lot of money. In our case, we invested a lot to build a 120,000-pound deadweight force stand. The United States Air Force, the United States Army. There's some other primary reference laboratories that have this same type of capability. And then we go down from there, we go to the accredited calibration suppliers. They use secondary standards, those calibrated by primary. This is for force. We have a webinar on ASTM E74 Explain that defines this a lot better. Basically, a primary standard's dead weight, a secondary standard is one that's been calibrated with primary. That's pretty the simplistic way to explain it. Then we have working standards, and they're working standards and certified reference materials used in commerce and industry, and they're traceable to all of the above. And then at the end of the day, we have field measurement, and these are typically the material testing machines used for tensile, compression, fatigue, impact, rheology, structural materials, or a range of other force application. Lots and lots. So we have all this, and this establishes really the traceability for field measurement on up. And then we're going to look at what does that mean? What does this uncertainty band mean? Well, it's usually defined somewhere on a scope, accredited, the ABs come out and they accredit people. They specifically, they want you to do a CMC, which is a calibration and measurement capability. And I borrowed this from A2LA R05 because I like this. It's the best I've seen. It's not just throwing every load cell specification in there or every manufacturer specification, which really may not mean anything to what or how you're using the instrument, where these do. So the CMC, it includes the following uncertainty contributors: repeatability, resolution, reproducibility, reference standard uncertainty, reference standard stability, and environmental factors. We have a paper on this if anybody's interested. It was just published in CalLab, and there's a link on the website. I can also send it to you if you're interested on how to derive CMCs for force. The paper goes into a lot of detail. And to remember these, if you're doing a budget, the easiest thing I can say is it's 5 R's and an E. It's pretty simple. But if we look at this in more detail, if we examine the CMC, here's a picture of an Excel spreadsheet. We have this online. If anybody wants this, they can go online and grab it. But if we examine it, so Morehouse primary standards is the reference CMC. If you look down here, Morehouse down here where I'm highlighting, that's the reference CMC. And this uses the Welsh-Satterthwaite equation. So we're going to take the degrees of freedom, we're going to take the types, we're going to take the standard uncertainties, and we're going to get a percentage contribution in here, and we're going to determine what our coverage factor really needs to be to ensure 95% confidence. Down here in this particular example, this number would be multiplied by 1.97. Lots of people say, hey, K equals 2 for 97. K does not always equal 2 for 95% confidence. It all depends on how these numbers are calculated. There are some cases where you don't have a large sample size, where you only do one measurement, repeatability measurement. Your K value might be 3.4. It might be 5. It just depends. It should be run through this Welsh-Satterthwaite equation. The important thing here is our CMC is 0016. We're looking at a 10,000 pound test point, and what this amounts to on this particular test is 14.43% contribution. Now if we look at the next level down, the accredited calibration laboratory, if we look at theirs, remember I said 0.2%, so that was this one standard deviation. 0.4 would be 2. If we look at theirs, it's 4%. On this particular load cell, calibrated in accordance with E74, if we look at that load cell, reproducibility, repeatability, resolution, all these factors are staying the same. And if we look at what happens when you go to an accredited calibration supplier, it's the expanded uncertainty becomes 4.03% with a 95.74% contribution. If those are wondering why is reproducibility blank here, it's because we're using ASTM E74, and the lower limit factor is really a pooled standard deviation that tests reproducibility. So it's, instead of double dipping, we're using this, and we're doing this. The paper explains it much more detail. So we examine this. If we look at it, us versus the accredited cal supplier, expanded uncertainty on a 10K cell that we calibrate could be as low as 0.41 pounds, whereas the expanded uncertainty on the accredited calibration supplier needs to be 4.0, could be as low as 4.03. Why is this? We're doing the same cal. It's because the uncertainty of the reference has to be included in the uncertainty budget. This is back to that traceability chain. You have to, for every step on that pyramid, you have to absorb the lab above you's uncertainty. If you do not absorb it, it does not work and it breaks down. So this is a case where the expanded uncertainty when calibrated with primary standards is approximately 10 times lower than using secondary standards. If we look at it in more detail, really what we did, if we want to do a CMC for ASTM E74 calibrations, you'd need the calibration report for the device, the uncertainty of the instruments that were used to perform the calibration, that's the reference standard uncertainty, the calibration history, the manufacturer's specification sheet, other error sources if they're known, and then the end user. You can get all this, typically you can get all this from us, and then the end user, if you're the one using this device, you're going to have to do repeatability study, you're going to have to do R&R between technicians. That's pretty easy. You can use Excel and use an ANOVA analysis, and then you're going to have to complete the proficiency test requirements by the standard. What's interesting about these PT requirements is you can do those. You could just send an artifact to NIST, you could send an artifact to us, you could send an artifact to another lab using deadweight primary standards, and you could complete the PT requirements yourself. You do not need to use accredited PT supplier just yet. They may change that, but right now, if you just need to demonstrate proof that you're doing it. That Excel sheet that we had for this, all of that is online. Again, if you get the PDF copy, you can go there. It's these little red tabs off here, if anybody's looking, or my highlighter, where I'm highlighting here. These little red tabs will explain what everything is. So you just go up to them, highlight them, and it'll tell you what goes in there, what it is, and what we're doing. I made lots of notes on that to help you guide through the process. And then finally, we get to measurement uncertainty and measurement risk. We're going at the ANSI NCSLI Z540.3 standard, and it defines measurement decision risk as a probability that an incorrect decision will result from a measurement. Here's a graph. You have your lower spec limit, that's this red line right here, and then you have your upper spec limit, and that's the red line to the right. The green is your nominal force point. So you draw that graph, anything that's that normal distribution graph, anything that's to the left or to the right of those lines is risk. This is a case where you have over 30% measurement risk on this particular graph. If anybody's okay with that, there's something wrong. You need to come into the measurement risk webinar, because that's just too much risk on a particular instrument. If we look at this graphically, what does this mean? You know, we start looking at risk, then you start talking about test uncertainty ratios. If we look at this same scenario graphically, a TUR done by primary standards on this equipment is going to be about 22.72 to 1, whereas that secondary force lab is going to be about 1 to 1. And it all depends on what the specification limit here is. This one's 0.5%. Actually, this one's 0.5. So in this example, the instrument read 10,000 when 10,000 was applied. What do you think happens when we move the location of the measurement? This, for those that have seen the measurement risk webinar, this will be familiar. What happens is it goes out. So even though you may think it's still in specification per manufacturer spec, the measured value, when you move that, you move all of that error curve. And as you look, the same over here on the left, TUR22, and the total risk is still 0. We've moved the location from 10,000 to 10,004. Over here, moving that location, it takes the risk up quite a bit. We get a total risk of 34.47. So it takes that risk from 4.55% to 34.7. So that's the difference from a lab with a CMC of 0.5 to a lab with a CMC of 0.016. And again, it depends on what your tolerances are and what you need. This next one has a better TUR table. If you're concerned with lowering your risk, take the measurement risk webinar. We have papers on that. Have the calibration provider replicate how the device is being used. That is the most important thing. Have competent technicians. That's almost equally important. Use the right equipment. Lower your uncertainties through your calibration provider. And there's quite a bit of difference between CMCs of 0.1, 0.5, 0.2, and this table really shows you. This table is based right here. This table is based on a calibration grade load cell with a 0.01 pound resolution and 0.05 pound repeatability. So those numbers go into that TUR equation, and this comes back depending on the tolerance, depending on the TUR test uncertainty ratio. So that brings us to this question. Most people, I gave this question, a room full of engineers, and they all answered yes. This is the problem with the basic community. Not enough people understand things. So if I have a 10,000 pound device with an accuracy of 0.1% of full scale plus or minus 10 pounds, my calibration certificate says the unit reads 10,000 pounds when 10,000 pounds was applied. Is my device in tolerance? You have zero error here. But when we calculate standard uncertainty and draw our curve, the plus or minus 10, the answer really depends on how good is my calibration supplier. Can they say whether this is in or out? How good is that true TUR and standard uncertainty? So again, this is a case where the total risk is 12.39%, much higher than the 2% required to be in tolerance. So if the measurement uncertainty is not being reported properly by your service provider, there is no way to know if the device is in tolerance and you do not have a traceable measurement. So again, if you have a cal cert, that uncertainty, regardless of what parameter you're in, that uncertainty of the reference needs to be reported. And this scenario I liken to, using a ruler to calibrate a gauge block. It's not feasible. You can't get the answers you want. So going back to force measurements, what could happen if you fail to get the force measurement correct? Well, incorrect concrete strength measurement, incorrect steel strength measurement, cables not checked properly for pre-spec or post-tension, all can be major, major problems. This one led to a bridge collapsing. So the next step is competence. The laboratories or bodies performing, next element is competence. The laboratories or bodies performing one or more steps in the chain must supply evidence for their technical competence. This is by documented proof. The service provider is accredited. The importance of this: if the laboratory staff performing calibrations do not know how to calibrate a device, i.e. using improper adapters, not aligning the unit under test properly, and improper loading procedures, are they competent? Can there be confidence in the results? How to provide evidence of competence? You can do this by proof of training records, on-the-job training, evaluation by management. It's still, the problem with that is it's still questionable. It's self-declaration. ISO 17025 accreditation is probably the best evidence. It's not the only evidence for competency, because the auditors do not check for everything. R&Rs to make sure people are your technicians. There's not a statistical difference between technicians is good. Other things, just blind tests where you send an instrument through, have several people calibrate it, and make sure all the results are in. There's lots of good ways. Checking the records, checking if they're following the procedures. Very important. So calibrating an artifact with primary standards and then performing an ILC is the best way to ensure that you are making measurements within your stated calibration and measurement capability. This is always going to be the best. If you can go back to primary standards and have something calibrated, you know the error band and what that should read, you can come back and make sure and compare and do some EN tests in the proficiency test. That Excel form also has a sheet for proficiency testing and ENs if you grab it. So some examples of competency include using proper adapters when calibrating force instruments. Improper adapters can produce errors 10 to 20 times that of manufacturer stated accuracy. Proper alignment of the unit under test, adapters and proper methods for loading threads. Misalignment, different hardness of adapters and thread loading versus shoulder loading can contribute to a decrease in repeatability of measurement results, resulting in additional measurement error. We're going to talk about some of these. I have 3 examples, so we're going to talk about those, what different adapters mean. Some will be familiar to people that have had the other webinars. There is a new one that you haven't seen before, and two will be familiar. And then we have repeatability and reproducibility test, as well as proficiency test, are good methods for detecting measurement errors. So if we look at this, we have tension link. There's a tension link, and there's a potential error source here. If you look at the picture, you can see to the left, this one's loaded without the proper pin diameter to 50,000 pounds of force. Sometimes these are referred to as load links, dynamometers, or crane scale. But look at the reading over here. If I highlight this, 49,140. So what about loaded with the proper pin diameter? We're engaging more of the instrument. This should be on a 50,000 pound device. This should be a 1.97 inch pin, or 50 millimeters. The best way to engage this device is to use it with the shackles that are being supplied with it. This is a case where that was not set in. We did some testing. The majority of the shackles on this instrument are going to be 1.97. Some may think, oh, I'll just use a 2-inch pin. A 2-inch pin will throw it out of tolerance. So I want to get that out there for anybody that's listening. Try to use what the customer is using, what they're calibrating with. Try to get those pins and calibrate it with those pins. If you cannot, you need to match the pin size as close as possible. There is a difference between a 1.97 pin and a 2-inch pin. So this one, manufacturer's accuracy specification is 0.1% of full scale. What if you're using a device like this for critical weighing application? There's the right pin, there's the wrong pin. Look at the difference here. We have a difference of 860 pounds, or 1.72% error on a 0.1% device from not using the proper load pins. A severe out of tolerance versus intolerance condition. And I must say that tension links of this design seem to exhibit similar problems. If you're unsure, you need to test it. That's the simplest thing. The majority of tension links we've seen, manufacturers will specify various pin sizes, so you really have to get back to the customer or the end user and figure out what they're using it with, what size pin, and try to get their shackles. So the next thing we discussed is misalignment. To the left, you can see we're aligning an S-beam. S-beams are good. They have problems. Some people like to use them as standards because they're cheap. If you align everything, you'll get a very good output. But then look to the right. If you look here, over here in the right, and look at the positional line, this thing's not really. Here's a good reference point on the cable. It's really not misaligned all that much. So here we have almost perfect alignment. We used a we used a scale, and then we just shifted it just a little bit, and by shifting it a little bit, you can see that line of force going up and down. If you just shift it a little bit, and look at the difference in output. We had a difference of output of 1.96732 versus 1.98211. Now this is millivolt per volt. What does this mean? That's a 0.752% error. Are your techs good enough to get that thing perfectly aligned? Is the person in the field, if they're using us for field measured, are they going to get this thing aligned? Probably not. It's probably not the right cell for the application, depending on what that application is. If you're locking it somewhere in place and doing a calibration, we see that a lot, then these are very good. But if you're moving them around or trying to use an S-beam as a standard to calibrate other things, it gets quite difficult pretty fast to maintain that alignment and not incur additional error. So what does that mean? So if we look at this, individual contributors, typically an S-beam calibrated to ASTM E74 is on the left. We look at what's going to happen. We aligned everything, we rotate everything properly, lined it in the machine. The expanded uncertainty of this is when it leaves our facility. I say the expected performance is another term that we could use. How good is it going to be for you, assuming that you can follow the same procedures and align it as well as we aligned it? Well, that expected performance or the expanded uncertainty is probably going to be around close to 10 pounds. But okay, so tech gets that, and then they do not align it. They misalign it. And look at the contribution for misalignment here. So that device that comes out of here that with an expected performance from us of 10 pounds, as soon as the tech does not align that properly, the expected performance or expanded uncertainty here goes to 85 pounds. It's quite a bit. If you think you're making a measurement and it's good to 10 and the tech's misaligning, it's really only good to 85. So it's really, that's something to be aware of. And it's keeping the line of force pure, free from eccentric forces, is key to the calibration of any load cell. And here we go, there's a side loading here, and then the actual load line. We want to follow that blue line. This cell, love the shear web cells, the shear web type designs. If they have an integral adapter installed, they're much better than if they do not. This cell, the misalignment, if we did the same thing we did with that S-beam, the error source would be around 0.002 or 20 to 22 parts per million. Versus it's dependent on the equipment. This one is not susceptible to misalignment errors, where the S-beam is very susceptible. So let's talk about something else. Let's talk about different types of adapters. So here's a test that we did with two different types of adapters and recorded the readings with 10,000 pounds applied. The output with the adapter to the left was 10,001.5 with a 1.5 inch of engagement versus 9942.3 with a half-inch engagement. There was a difference of 59.2 pounds on a 10,000 pound cell. So, this error measurement was over, 0.5%, which is better than, how are your devices being calibrated? If we look at this, and we looked at this in more detail, this is a Sensitech load cell, two different types, and we graph it. So let's, look at these graphs. The one on the left is with the right adapter. If the customer replicates that, they should be well within 0.25%. But if they switch at top adapters on that load cell, they're nowhere near. If you look at this graph over here, measurement error 57.7, total risk is 100%. This is the line where they want to be right here. There's no way near. You know, I say, what is the probability of the measurement being within 1/4% if the top adapter is changed out? I think this graphic shows it all. Hopefully you get a kick out of it. Anybody looking at this, yeah, the chances are the same as when hell freezes over. So another error source, when I mentioned earlier about that integral adapter being locked in, I did a lot of tests on that. So the top gray line shows the difference in output when using a shear web load at different thread depths. Love the shear web load cell, hate them without the adapter locked in. The darker bottom line shows the difference in output when loading against the shoulder. So basically here, we can take different thread sizes and different adapter types down here, and as long as we load against the shoulder, we should have a relatively, the difference should be around 0.1% error, not as large. But if we just vary that depth and we do not load against the shoulder, we can have quite large errors rather quickly. The solution is to lock this in place. You put one of these adapters in place, lock it in, never take it out, use that with the load cell for eternity, and you will love the measurement results. Much more repeatable. It eliminates the thread depth problem. 100% of the time it's repeatable. So again, this is a picture of a Morehouse threaded adapter with jam nut permanently locked into the load cell, and it's going to eliminate all the errors. You're not even going to have the 0.01 loading against the shoulder error. So highly recommend that. If you have one of these cells, lock an adapter in, it will get better. So then we go to number 5, and 5 is documentation. Each step in the chain must be performed according to documented and generally acknowledged procedures, and the results must be recorded. Per ISO 17025 5.4.1, the laboratory shall use the appropriate methods and procedures for all tests and calibrations within its scope. The importance of this: the calibration must be performed using acceptable agreed upon calibrating method or procedure. This is done in contract review. The result must be provided in a report with necessary information. The worst thing you could tell somebody is calibrate to manufacturer specifications, because no one knows what that really means. Does that mean I should be monitoring linearity? Should I be looking at repeatability? Should I be looking at temperature creep? Manufacturer specifications, if you were to do all the calibrations on their spec sheet, it would cost an absolute fortune to verify them. It's just not practical. So the better thing to do is say, hey, I need this thing. I'm using this. Maybe I'm using this load cell increasing only. I'm concerned with my non-linearity, and I'm concerned with repeatability. I'd recommend E74. I think it will take away a lot of that error, but I know that's not acceptable to everybody. So yeah, get the specifications that you need, put it on the contract, and be sure to tell the laboratory what those are. So what could go wrong? Procedures not validated that do not cover all parameters and ranges, partial or limited calibration. This includes software. Results not purported accurately, clearly, unambiguously, and in accordance with the specific instructions in the calibration method. You know, labs often fail to follow the standard properly. Here's a E74 example. You know, you look at what's wrong here. It looks like a good cert. But if you read the standard, this lab's not following it. And the standard basically says, section 8.6, the loading range shall not include forces outside the range of forces applied during calibration. So what's the loading range? Down here, 192.3 is the Class A lower limit. So this is the loading range. So 192.3, was that applied during calibration? No. 0 was the first test point, and then 500 pounds was applied. So we look at that and we say, okay, some people say, yeah, 0 is acceptable, but 0 is not an acceptable first point, because section 7.2.1 of ASTM E7413A states, in no case should the smallest force applied be below the lower limit of the instrument as defined by 400 times the resolution. So in this case, this cell has what appears to be a 0.1 pound resolution. 400 times that is 40. So the lowest first test point should be 40 pounds is the absolute lowest. In this case, this calibration is not valid. The first test point that the end user can use this cell at is the 500 pound point. And really the only thing that needs to happen to the certificate is the Class A lower limit has to be up to 500 pounds, and then everything would be in compliance. We get to number 6, which is calibration intervals. You know, a lot of people have problems with this. You can do end of period reliability studies. You can do other things. Is it 90 days? Is it 1 year, 180, 3 years? It all depends on what your risk level is. Calibration must be repeated at the appropriate intervals. The length of these intervals will depend on the number of variables, uncertainty required, frequency of use, condition used, stability of equipment, all these things. ISO 17025, current standard until the new one comes out, the section 5.10.44, a calibration certificate or label shall not contain any recommendation on the calibration interval except where it has been agreed with the customer. This is very important. We as a Cal Lab cannot assign the interval of your equipment. We can discuss it with you. If you're calibrating in accordance with ASTM E74, the standard has criteria to set the dates, but in general, somebody sends in a load cell and says, do a 10-point calibration, all I care about is nonlinearity, send it back to me, we report nonlinearity. We have no idea on what interval that needs to be set to. That's something that you need to look at the stability, do the CMCs, and figure out what the appropriate interval is for your risk level. The importance of this is if an inappropriate calibration are used, the reliability of the results reported are questionable. We saw this the other day. Somebody, ASTM calibration, they waited 4 years between calibrations. They're not allowed to do that per the standard. They did it, and their stability, of course, grew. What they were claiming as the CMC and what their actual CMC was were two different things because of that stability. So profitability can be reduced if the intervals are too short. That's another thing. If you don't have the right equipment and you have to have it calibrated every 2 weeks to maintain what you need, just get new equipment. We like to do a calibration every 2 weeks, but it's just senseless. Getting better equipment can often result in an increase of profitability and increase in that cal interval with nice stable equipment. It's always funny up front. Somebody will see an equipment cost of $800 versus $1,600. They go with the $800 option, and it'll cost them 4 or 5 times more in calibration because they'll have to have it calibrated every 6 months instead of every 2 years or every year. So the frequencies will just be double or quadruple. What could go wrong? Inappropriate intervals can result in unknown drift, increased measurement uncertainty, and incorrect claim of MU reported. The case where the 4-year interval happened, the incorrect claim of MU was reported. So if we're looking at ASTM, some people are interested in this standard. The calibration interval is pretty fairly defined. It's a secondary standard, should be calibrated to ensure that they do not change more than 0.032% over the loading range. And then the instruments that are used for Class A devices should not change more than 0.116% over the loading range. If the entire loading range, if nothing has changed by 0.16% over that loading range, then ASTM allows you to set the calibration for 2 years for Class A loading range, and if it hasn't changed by more than 0.032% for Class AA, then that can go to 2 years as well. Class AA, it's recommended that it be a little less, but it allows you to do it if it meets 0.032. Now we get to the final number here, which is measurement assurance. Measurement assurance is practices put in place to monitor a testing or calibration process and to ensure the calibration status of equipment. Reference standards or reference materials used in a measurement process. This is great. If you have a measurement assurance program, it needs to exist for each step in the measurement hierarchy to ensure the competency of the measurement results. So you're going to have to, are your measurements traceable to SI units? Are you calculating your measurement uncertainty correctly? Are you doing all these things? Are you competent? Are you documenting? All of this needs to exist. Checkbox. I like to say, measurement assurance. A good thing you can do is SPC. Hold everything together by having good artifacts to constantly check your equipment at whatever interval it needs to be tested to ensure that it's not drifting out. So other things you can do the proficiency testing, interlaboratory comparisons, ILCs, intermediate checks. You could send a load cell, 2 load cells to us and use one as the standard to verify or check against to meet the proficiency test requirements. You can use a load cell to do that same load cell. You could also use to do your statistical process control. Put it up in a machine, check it every month, document what you're doing. So if we go to section 5.5.2, 10, that specifically states when intermediate checks are needed to maintain the confidence in the calibration status of the equipment, these checks shall be carried out in accordance to a defined procedure. Well, SPC is a defined, SPC here, you can write a SPC procedure, that is a defined procedure. So again, statistical process control, very good. We have a class on it May 10th. Consequences from the lack of measurement traceability. Well, you have profit, you have risk, and you have loss. So without all 7 elements in place, your measurements are not traceable. That's a problem. That puts you out to possibly recalling lots of equipment. What measurement errors do, they raise the risk level for product failures, false accepts, and false rejects. I suggest anyone that wants to know more about this read the measurement risk paper or take our webinar on measurement risk. If taken to court, the question that you have to ask yourself, we are a very litigious society, but you have to ask, are your measurements defensible? If you are missing any elements in the measurement traceability chain, they're not. So if the quality manager says, yeah, these measurements are good, and you know they're not, now for ISO 9000 2015, the quality manager is going to get in trouble. And I believe the 17025 standard's going that same way, where there's more responsibility put on the quality manager. So my son has a professor. He always says, we're not going to have a test, we're going to have a celebration of knowledge. Always cracks me up. So just a quick review, the 7 essential elements of traceability, reference to International System of Units, an unbroken chain of comparisons, measurement uncertainty, competence, documentation, calibration intervals, and then what we just discussed, the measurement assurance. And metrology is not meteorology. Type it in Google. Google's going to tell you spelled the word wrong, even though Google tells me metrology is not a word. And to get back to a serious point, if you do not know how the instrument should be calibrated, what should you do? So let everybody think about this one. Hopefully you picked up on it during this presentation. If you do not know, you need to contact the user. I don't know why people avoid doing this. It's like the user is whatever. You need to contact the user and find out how the M&T measuring and test equipment is being used. And that is number 5, which is documentation contract review. Needs to happen. It's sometimes, I know it's hard to get through purchasing in big companies, or it's hard, but you need to get to that end user. Otherwise, you could have a situation where you think the end user thinks they're using a device to 0.1% of full scale when someone used different pins and they're at 1.72%, and that's going to mess up every single measurement they do. So with that in mind, May 16th, we have a free webinar on measurement risk at 11 a.m. Upcoming course schedule here. If anybody's interested, these are paid courses. We have Advanced MU, May 11th and 12th, $750 per person. Force Fundamentals, that's a 2-day class. That's May 8th and 9th. The course typically runs 8:30 to 5. We will go longer, or we will start earlier. We will answer any questions related to force during this. Typical days for this run really 8 to 6 to some people. Some people just want to get all their questions answered, and we are happy to do that. And then we talked about measurement assurance here in SPC class. So the SPC and the force fundamentals are also scheduled for October 3rd and October 2nd, October 3rd and 4th and October 2nd. The Advanced MU, this is the only time this year that we are running it, and that is May 11th and 12th. There are still spots left for that. Force Fundamentals, we moved to a larger hotel with lots, so we have more, we can accommodate more people, so we have, that's open, and SPC, we have, I think, 2 seats left in that. If anybody's interested, just send an email, I can talk, or give me a call. So we get to the end. Thank you, everybody. I'd like to take questions. If you want to learn more, we have a blog. We have a new blog on making statements of compliance. Wrote that about a week ago. Explains what's needed to make a statement of compliance, a pass, fail. There's some instruments where you cannot make a statement of compliance because the risk is too high, and it's sometimes that's instrument dependent. With instrument has resolution that's too coarse, or the instrument does not repeat well. And if anybody's interested to sign up for a newsletter, you get about quarterly mailings on when we have these webinars, when we have new blog posts and other things. So please do that. So I'm going to open all the mics. Really receptive to questions right